All right, so I guess this this talk deals with some questions that I had about how to do cool things maybe like a year ago. And what I wanted to do was, so I've dabbled in robots that make things. So I built a 3D printer, but that wasn't really super impressive because I just sort of followed a lot of instructions. So I figured, how can I figure out more things? And I thought a really cool project to do would be to have a little robotic arm. Oh, that's not going to give you what I want to convey. Have a little robotic arm that stays in a plane and has a little pen here and can draw pictures on a sheet of paper. And I figured that would be pretty cool to do, and kind of delved into a few things and got a lot of interesting math out of it, actually. So this is going to touch a little bit upon computer graphics, things called SVG files, which is a way to represent a picture, but not by pixel. It actually describes curves in the picture, which makes it much easier for me to draw them. And it'll talk a little bit about some transforms of space, and then how I actually ended up approximating it on this. And I'll show you a simulator that runs this arm. And I would show you the arm, but I built it, and the power supply caught on fire, and it's now in pieces at my parents' house. So, does anybody have any questions or anything yet? Yeah?
Doesn't Wikipedia do signatures as SVG files?
Probably. They do a lot of things. Actually, all of their biological diagrams are all SVG files. Okay. I know that. But yeah, I'll talk a little bit more about SVG later. But they probably do, so we can forge signatures with this. Anyway, so I guess this kind of has a few mathematical questions. First of all, I decided to have two little arms here, and I made them both the same length, which we'll call A. And so here's a good question which I had, which kind of started the whole thing, which was, if I have a point x, y, and an angle phi and an angle theta here, how can I go from this to this and back again? And it's relatively immediate trigonometry, but we can play around with it for a little bit. Maybe it'll get the math started, and then it actually yields something really cool when we're done, so I think it's probably worth it. So anyway, let's break this into two right triangles here, and we'll see that now. So this is a right triangle. So now this portion of this angle is pi halves minus. I wrote this down. It's really silly, but I'm gonna mess something up, and somebody's gonna yell at me. So this angle here is pi halves minus phi, and then this portion is theta plus, I guess.
It would be theta minus the angle.
Right, yeah, theta minus, theta plus phi minus pi halves. Thank you. So if we want to say we're given these angles, then we can split this up into two different, into some trigonometry. So this length is A times cosine of phi, and then this length is sine of theta plus phi minus pi halves. One of the lesser used trig identities, this is equal to cosine, negative cosine of theta plus phi. So this whole length then, x from the origin to here equals...
That would be multiplied by a, right?
Yes.
Yeah.
Equals a cosine phi minus cosine, cosine theta plus phi. So relatively straightforward. Same with the height, except now we're actually subtracting. So this height is sine of phi, and then this is sorry, I have horrible board presence. Cosine of our old function this, or our old angle this, the blah blah blah. Halves. And so this equals sine theta plus phi, but we're actually subtracting it, so y equals
You mean sine in both scenarios?
Yes, thank you. Copied a little bit too much. Here we go. So this will give us a nice little map. I'll just write it as an actual vector. F of phi theta equals and now, sort of to invert this, we can't. This is not necessarily easy to invert by itself, but let's take a look at this. So we have x, y, and we want to determine phi and theta. So this stumped me for a little bit, but what I ended up doing is, this is an isosceles triangle. We can use the law of cosines to determine this angle, and then split it up here. But I'll show you in just a second. So we can use the law of cosines, which I believe the statement of the law of cosines is if we have a triangle A, B, C, alpha, beta, gamma. C squared equals a squared plus b squared minus 2ab cosine gamma. So we just plug this in here. We don't really care about angles. This is the only angle we care about. We get so x squared plus y squared, which is the length of this side, squared. So yeah, by Pythagoras. Equals, and then a squared is a squared plus a squared minus 2, again a squared, times cosine, and in our case this is theta. So we end up with theta equals, well, cosine of theta equals 2a squared minus x squared minus y squared all over 2a squared. Then theta equals our cosine of this. And then, is everybody okay so far? All right. Then we can get phi. This is isosceles.
One sec.
Yes.
So your theta in this scenario is guaranteed to be only from 0 to 180 degrees, 0 to pi?
Right, yes.
Yeah, because if there were multiple solutions, then inverse cosine wouldn't necessarily give you the right one.
Right, yeah, it wouldn't necessarily. So, right, so what I've done is I've assumed this angle is always facing like this. We could also, of course, have this triangle here.
So the arm's not bending backwards.
Right, the arm is not bending backwards, right. So it's like an elbow. Actually, yeah. Thanks for reminding me of that.
Mm-hmm.
So now we have a phi. I don't know who would call that a phi. I certainly wouldn't. So phi then equals. We'll split this angle. And we get pi minus theta over 2. So everybody follow. These angles are equal, and then we will.
Maybe in pi minus
yes,
theta all over 2.
Pi minus theta all over 2. Certainly. Plus our tangent of y over x. Because, so our tangent of y over x will give us this portion of the angle, And then this is given by pi minus theta all over 2. So we'll add those two to get this, and then we can expand this. So we'll get f inverse x, y, and I'm going to copy this to make sure I don't make a mistake. So now we have a function in its inverse. And so today, while I was going over the math for this, well, okay, so what have we done so far? So now we can move from these sort of angular coordinates, so what's the angle of my shoulder, to the angle of my elbow, to the position of my hand, and we can go from position of hand to angle of elbow and angle of shoulder, which is pretty neat, assuming that my forearm and my shoulder are the same length. Or in my so now there's sort of an interesting question of what happens if we move, say I want to change my angle of my shoulder linearly, and I want to do the same to my elbow. So what kind of curve does my arm make? So if I increase at the same rate, both of these angles, what happens? And what this looks like is, so we'll take a little square and we'll call this phi theta space. So this is where our angles live, and we want to map this using f into xy space, which is where my hand is, and we'll just take some sort of straight line in here, and to make it easy, we'll pass it through the origin. So this is the origin, and to make it even easier, why don't we say that they increase at the same rate? So this passes through 1, 1 at some point along our line. Is everybody with me? Anybody have any questions? Okay. So I just figured this out today, and I thought that it was really slick. But let's see. Before we do this, I'm gonna sort of show you what this looks like, and then we'll talk about it. So now would be the time to ask the specially prepared questions I mailed out to the room. Yeah, nothing. Sorry. So does anybody have an idea of what this might look like? Any sort of question? Any thoughts about what it would look like?
I'm gonna guess like sort of outward spirally.
Yes, like an outward spirally. That is perfect. That's almost exactly what it does look like. Does this plug in here? Somebody told me my computer science major is giving me some semblance of this. Yeah, thanks.
Light is going on.
Light is going on?
Yeah.
These are good things.
The screen switches over.
Yep. Ah, I see things. Hey! Alright. I think that's the quickest, the most cool way. Can we turn the lights off? Imagine. Alright. Let's see. I know I do, yeah. Yay, okay, so it drew something. So that's pretty neat, right? But let's hear
That
this.
was my constant break.
Sorry?
Don't think that was done at constant.
No. So right. So let's move our hand here, and then let's pick a point maybe out here that we want to move to, and the way that this works is it'll move linearly. So right, that looks very spirally, right? Let's do that again. This thing goes into infinitely recursive loops if you click inside that circle. There it goes. Sorry. So if we move all the way up here, right, that looks quite a bit like a spiral, but why isn't that a spiral? So I was like, oh, this is great, this is exactly a spiral, but it can't be, because why? So if we were to keep drawing forever, what would happen? We can only extend our arm a certain length, right? We don't have like a telescoping elbow. So what does this actually look like? Does anybody?
Is this the path of one object chasing another going in a circle?
You could say something like that. Yes. Yes. Essentially.
Is it cycloid?
It's not a cycloid. It's it actually ends up being something very close to a cardioid. Which I discovered today. So you're very close. So a cardioid you can define as, I'm going to put this back up now, as a circle. Can I make this black or do I have to turn it off?
Not sure these have black screen.
That's a shame.
I've sometimes had a picture loaded that's just totally black on my computer.
Yeah, that's useful. So I should have thought of that. So a cardioid. So I said this looks like a cardioid. No, what does that mean? So I'm gonna erase this. So a cardioid is if you take a circle, and you have another circle, and you fix a point on this circle, right? And then you roll the circle around. Does that make sense? So you roll it around, and you track where this fixed point moves. So it'll move out here, and it'll touch there. You can imagine this thing has now completed one full cycle, and then it comes back here. And it's called a cardioid because it looks like an apple. No, it's called a cardioid because it looks like a heart. So anyway, so this is a cardioid, and so I was playing with some math today, and so what if we'll take this line, and maybe we'll call it alpha of t, so just we have a nice little parameterization, and we get t comma t, so what does this map to over here? So let's take, oh wow. So let's take, what is f of alpha of t? So what's f of our line? So what does this line map to in xy space? And so this equals f of t comma t, which equals, ends up being, and so if you look at the equation of a cardioid, so let's say we have a cardioid beta of t. If we parameterize that in the Cartesian plane, we actually get 2a cosine t minus a cosine of 2t, and then the same thing for sine. So this thing is not quite a cardioid, but it looks very close. It's in a family, the name of which I've now forgotten, but which includes cardioids. So I thought this was really, really interesting. So what happens is we'll take this line in phi theta space, and it ends up mapping to a cardioid here. And so there's our equation, or not a cardioid, an almost cardioid. And so now this sort of brings the question of, David, you're drawing curves, you're not just drawing apples here. So why do we care? And it's really because computers are not good at math, really. They're good at discrete math. And so this computer has no concept of oh, we need to draw a curve, so we're going to change our elbows at this specific rate, and it's going to be a continuous function of how quickly we're moving our elbow. Instead, we need to break up the curve, and breaking that up in the most logical way would be, where both motors are moving at some speed. So what we're doing is we're actually breaking up these curves into cardioid parts, or almost cardioid parts, which I think is pretty interesting. So now this is going to be a little question about how do computers represent curves? And so has anybody heard about Bezier curve? It's spelled Bezier. Bezier. And there's an accent somewhere. Does anybody know? Nope. All right.
It would probably be Bezier.
Put it there. Yeah. All right. So Bezier curves. And these, if you've ever used Photoshop and you have a curve and it has some little lines on it, like this, and you move the lines around and you get different curves. So if we move it here, we'll get that curve. If we move this one down here, we'll get this curve. So that's what a Bezier curve is. But these are pretty interesting mathematically. So we'll talk about, so first of all, a line is a Bezier curve. It's called a linear Bezier curve. And what you do is you'll define a point and a direction for that point. Which is all well and good. So really you're defining 2 points, a point and another point, and then you draw a line between them. So that's a Bezier curve. But the Bezier curve parameterizes that line. Now a quadratic Bezier curve, you take a point and another point, and then you have what's called a control point for the Bezier curve. So point 1, point 0, point 1, and then we'll call this point control. We'll call it point control. What happens here is it moves up along. It moves up towards the control point, and then goes back down and passes through point 2. And so vectors from the control point to each of our points are the tangent to the curve at these points. And this is interesting, but it obviously has to happen in some specific way. I mean, I could come up with a lot of curves that do this. So the specific way in which it happens is pretty interesting. So we'll take 3 points and we'll connect them. So this is again our control point, point 0, and point 1. I'm going to turn on the lights. So what happens is we'll track several points. So we'll have a t which moves from 0 to 1, and so we'll track a point along this line. So a point along this line will move, and a point along this line will move down here, both at the same rate. So at time 0, our first point is here, and our second point is here, and at time 1, they've now moved to here. Make sense? And what we're going to do is we're going to connect the points. So now we get a new line. So say we're at some t within that range. Now we've connected the points, and here we are. And now we're going to do something even crazier, which is we're going to take a point moving along this line at the same rate, and we're going to trace the path of this point. And when we trace the path of this point, we end up, so you can picture sort of maybe a lot of these here. So we're early on the line here, now we're rather late on the line here. And if we connect these dots, we end up with a Bezier. Quadratic Bezier.
So the point that's on the chord actually starts off on like the left-hand side and then moves along it and ends
Yes,
up. Okay.
right. So it's hard to show statically, but if we look at this line, as this line moves, yes, the point moves along the line. Yeah.
So for instance, like if t were 3/10, so 30% of the way across,
Right.
then the left point would be 30% of the way up.
Right.
The right point would be 30% of the way down.
Down, and
And then you'd go 30% of the way across the chord.
between the two. Right. Exactly. And we trace that 30% point, which then becomes 40%, and so on. And that's what a Bezier curve is. And really similarly, we'll have, say, a quadratic, or no, cubic Bezier curve, which is what almost all Bezier curves actually are, where you have this, and this gets really kind of scary here. So we'll have a line here. Oh, whoa. All right. So we'll have point early here, early on this segment here, and early on this segment here, right? Connect them. Now, we're still early on this segment and early on this segment, right? So we'll connect those, and now we're here. And this is the point that we chose. So as these things sort of move through space, it's like looks like a mechanical freaky snake. These go all the way up into a lot of dimensions. And when you get to really high dimensions and you move the points around, really everything kind of flattens it out and you end up with really smooth curves. But cubics are good enough, they're close enough for computers, which honestly isn't very close at all. So does everybody understand sort of the general concept of a Bezier curve? Any questions?
Is that where the Star Trek logo came from?
Yes, yes. The Star Trek logo looks like this, so I'm sorry. Maybe it's two Bezier curves stacked on top of each other. And you couldn't even parameterize this thing anyway, so all right, where are we? Oh, so we have all these Bezier curves. So SVG, SVG is something called scalable vector graphics, right? SVG. You might have seen a .svg, scalable vector graphics. And so these files, so they're called scalable because they actually just describe the curves in the file. So if you've ever taken like a JPEG file and you've blown it up really big, you can't like see anything and it looks like a map of the woods. It's just crazy. Well, SVG files don't have that problem because as you scale them up, they can just recalculate the image from all of the curves, and they have basically an infinite precision between boundary points. So scalable vector graphics. Now, scalable vector graphics define a lot of different things. So they'll define lines. They'll define quadratic Bezier curves. They'll define cubics. And they'll define circles and arcs. Now, circles and arcs, the way that they're parameterized actually gets really, really, really hairy. And so a lot of them are actually, so you can approximate a circle with a few cubics, and that's really the easiest thing to do. I'll talk about, just briefly, the reason that is you take 2 points and then you define a radius. So what would be really nice and happy is you pick 3 points, you've uniquely determined a circle, and then you pick which 2 points are the endpoints. Ta-da, or like so. That would be so easy, but that's not what happens. You have 2 points and a radius of the circle, and then whether it's a small arc or a large arc, and which side the circle is on. The math is really completely vomit-inducing. It's horrible. So if you have 2 points and one radius, you then can establish some triangles here based on the radii, and then we'll get some circles here and a circle here. But then now we're trying to find an arc. So which arc do we pick? There's actually 4 here. So you have 2 different flags. You want the small arc, so that's the small arc, or do you want the big arc? Doing that computationally is really a pain. So I'll stop talking about circles now because I'm not going to talk about them. So really what I'm going to talk about is first I'll talk about lines. So we want to draw a line with this arm, right? Now to do that, this would be interesting. I haven't done this math yet, but we could take a line in x, y. And go backwards from into theta space. Do you guys want to do that, or yeah? All right. So Daniel's going to lead the charge here. So this will be relatively easy.
It shouldn't be too bad.
Yeah. So
the numerator of the arc coast just comes to 0.
Yeah, I think it will. Yes, certainly. If our line is. Right. Yeah. So it will if we want to draw a line straight out, which you can imagine. So if I want to move my arm straight out, I can just kind of like punch outwards, and I never have to really. I mean, my shoulder changes, but it does. Yeah. Yes. But it'll draw a straight line if you go straight out very easily. I'm gonna stop trying to explain that. Yeah. So let's go backwards. And I guess we could do some sort of generally sloped line, but I think it might be easier if we just do the 1, 1 line. So we'll say this goes to 1, 1. Can I reuse alpha, Xavier, and throw out another letter? Oopsilon?
Squiggly.
Squiggly? Squiggle of t equals t in, now in xy space, and we want to move it backwards. So this will be interesting. So f of squiggle equals f of t equals, so let's see, so arc tangent of t over t plus pi minus arc cosine of 2a squared over 2a squared, so this goes to 1.
No, it's 2a squared minus 2t squared.
Yeah.
Oh, right, okay, certainly. So 2t squared over 2a squared, then we're done with that, and we get this again. Oh, no, we're not, I lied. Alright, cosine 2a squared minus 2t squared over 2a squared. So that's what that looks like, which everybody can immediately see what curve that maps to. I don't know what this looks like in phi theta space. Does anybody know off the top of their heads? We could graph it.
That's actually the structure photo.
That's the real structure. But I guess maybe where this gets interesting from a computer science standpoint is we can't actually do this. We can approximate this, and it's actually easier. So we could approximate this function in phi theta space and get a little bit off every time. And so what'll happen there is, say we want to draw a straight line, but we'll actually draw a little, well, here. So say we want to draw a straight. Too much gusto with that. Say we want to draw a straight line. So we're gonna draw a little curve here, right? But we're gonna be a little bit off. And then we'll draw a little curve here, be a little off, a little curve there, be a little off. And we'll actually move away from the curve because we're off in phi theta space. Yes?
You're doing the curves because you have the angles increasing linearly each time?
Yes,
All the
right.
time?
Right. So they're increasing on some line. So it doesn't have to be this line. It can be any slope. So my elbow can move faster than my shoulder and vice versa. But these are all going to make some semblance of these cardioid lengths. If that makes sense. I call them natural arcs when I figured them out, but they're actually part cardioids. So it's much easier actually if we take, and this actually has applications to computer graphics, which is pretty cool. This is how, so computers don't obviously have to work in these natural arcs. That would be completely silly. But they do work well with straight lines. So when they display something on a monitor, will display a series of a sequence of straight lines instead of the actual perfect curve. So let's say I'll talk about how computers do it first with real graphics. So say we have this Bezier curve. So we have two endpoints and obviously some control points, but we're not super concerned about the control points right now. What's important is we can get a very nice. So I haven't talked about this, but these curves are very, very nicely parameterizable. So we can have a really good parameterization. Somebody give me a letter. Gamma.
I vote for gamma.
Gamma. Okay. So this is gamma of t. And so what the computer will do is it'll say, well, let's just we'll just draw this as a straight line between the endpoints, and then it will measure. It will use some metric of, well, how much did we actually mess up by doing, which is often quite a bit. And so if, say, for example, our metric is we pick 50 points along here, and we pick 50 points along the curve, and figure out how different they are. And these curves are relatively smooth, and they don't jumped very quickly. So we might be able to do that. So if this is above some certain threshold, then this is a horrible parameterization of, or a horrible approximation of this curve. So we're going to split it in half. So now we're going to take a point halfway along the curve and do the same thing. Now for our case, that didn't help us at all because it's basically an odd function. But now what if we, so we do the same thing for each one of these half curves, and now we get this. Now that's much better, right? And we'll continue to do this. So each curve will split until that particular curve is within a certain threshold of the actual curve. And what's cool about this, so this is something called recursion, which maybe the computer science people in the room will know about. But what's good about this is it takes each curve as a brand new object. So when I'm looking at this curve, I'm not thinking about this curve or this curve or this curve. So imagine we have some sort of thing that goes like this. So it's a straight line here, and then it's a curve. So we would approximate like this, and then we would pick a point here, and do this, right? So this is perfect. This is a perfect parameterization. But since we're looking at each part independently, we're good. We don't have to waste a lot of computation here. So this is actually surprisingly adaptive to what we need to be doing. And
I think adaptive is the technical term for it.
right. Yeah. This is adaptive. Yeah. And so right. So now we have an adaptive method for doing this with lines. It's completely okay for us to do this with these little curves as well. So we have this, and so say our arm is here. So our natural curves are they're gonna all kind of go in this direction, right? Which means that this part is gonna be hard to do, and this part will be easier to do. Does that make sense? Yeah, okay. So we'll do something like this. We want to move straight out. Now this will actually look like a straight line in the arc because we can just sort of punch straight out. But then if we move here, well then our curve starts to look like this, and this curve will start to look like this. Nope, that's not right. Oh, it will. I was right. It'll look like that. And so we can continue breaking these down. So we'll just do exactly what we were doing, except instead of lines, now we have these cardioid parts. And so we bring them within a certain threshold. And then we can do cool things like have a sequence of points. So now this whole problem reduces to where did we split our curve when we did this. So for example, here we had this curve. So these points are going to be really quite densely packed in here. But then here, this more approximates a natural arc, so they'll spread out. And then here, again, our points get more and more dense. And so we can give this entire curve as just a series of angle measurements, where it can just move as naturally as it wants to. It can move with the motors. The motors don't have to do anything special between points, and this guarantees that they're close enough as long as it's moving between the points. And so you can sort of play around with the threshold that this gives, and then there you have it. I mean, this will give you curves. So you can just feed these points. Say, I want this motor to move until it hits this theta coordinate. I want the other motor to move until it hits the correct phi coordinate, and then you will have completed that tiny segment of the arc needed to draw that part of the curve. So that is maybe about it from me. I can show you how it works. It's kind of fun to watch. I don't know why I did that. What I wanted to do is this. Does anybody have any questions about this?
So is that computation pretty fast, obviously?
Yeah, it is fast. For really complex things with a lot of separate curves, it can get really not fast. So it can take a while, but that's all pre-computed. So you could, for example, pre-compute these and then just send in a list of points. And
Why does it loop infinitely over and over circle?
it doesn't loop infinitely. My threshold, I think, is too tight. It keeps splitting the.
Oh, right.
Yeah.
Yeah, that's what.
Yeah. Anybody else have questions? This is what's up. All right. So I think probably the hardest part of this whole thing to program was parsing XML, which actually doesn't work. So I hand extracted paths from the XML. XML is really bad as a game. Yeah, so it'll write my name. I was really surprised when this worked the first time.
Is he doing it with the least distance possible? Generally possible?
No, it's not. Certainly not. It's going way up. It's going so in the SVG file. These are specified in some order, the different curves, and it goes in that order. It's pretty dumb.
How'd you generate the SVG file for your name?
I just used Inkscape, wrote my name, broke it apart into paths, hand copied the XML out, and then right. So here's. This one's fun to watch, but it takes a long time to pre-compute. So, does anybody else have any questions or discussion or something? Because I'm really done, or we can just watch this. So you'll notice this thing will slow down. That's not a function of the algorithm or anything that's happening, except for the fact that this little canvas is holding tons of tiny little lines in memory and displaying them at every time step. It's a really bad implementation of a canvas. But what am I gonna do, you know?
So why is it thickening in some lines? Or why is it-
SVG. Okay. It's all in the file. So it will blindly do whatever the file tells it to.
You know, when I saw the file name, I knew it.
Yeah.
Do you have any? So when you had the mechanics working, did you get any cool pictures out of it?
I drew that A from earlier, which just about burned my house down. I'm much better as a programmer than I am as any form of electrical engineer. So I don't understand. If anybody really understands power supplies, talk to me. We can do great things. Great. So get in there. Oh, thanks.
You have to clap till the end of the picture.
How much detail did you put in this?
I didn't. I just pulled this from the net.
So if you get the electrical engineering side questions answered, then you're going to have a robot arm do this?
Certainly, and it will forge signatures too. I think. Yeah. But yes, it will.
So is this operating on like a time increment, or is this just going as fast as it possibly can to draw it out?
It's moving as fast as it can. So just as quickly as it can process loops in Python, it'll write the next segment.
There must be a lot of lines.
Yeah, and so what's really funny about this is actually, so this is a computer simulating a robotic arm, which draws these things. So remember I talked about computer graphics, so maybe you can see where this is heading. Is it will actually then break down these approximate paths into straight lines for the computer. So it does like a double recursion, and it's not very good. But it works. And now there's Mickey Mouse. So yeah, if anybody has any questions, talk to me. If not, I guess I'm done.